Jen Jong's in the lead. Ooh yeah, ooh yeah. Sasha's groove and dancing feet. That's right, Dr. Connie brings the beat. All night, all night. FOA, show the way. Let's go, let's go. Tutors know how to flow. We groove, we groove. Melbourne lights shining bright. We dance in the night. Algorithms advance. Binary, we code.
Hi, I'm Lenny. I have 100 students this semester and I'm going to try and remember all of your names. Welcome to Foundation of Algorithms.
Hello, well, I'm Casey. Welcome to Foundations of Algorithms. You're learning my favorite programming language this semester, C. Really hope you enjoy it. And remember, algorithms are fun.
Hi, my name is Charlie. My goal is to make you, by the end of this subject, all say algorithms are so fun.
Hi, my name's Endo. Trust me when I say that you're all going to have a blast this semester. And of course, algorithms are fun.
Hi, my name is Patrick. I hope you have an amazing time learning my second favorite programming language. And remember, algorithms are fun.
Hi, I'm Taha, and you'll definitely enjoy this subject because C is better than Python and algorithms are fun.
Hi, I'm Maria. I'm very excited to see all of you in class. Algorithms are fun.
Hi everyone, I'm Izzy. We're gonna have a super fun semester together. Don't forget, algorithms are fun.
Well, hello there. This is Tracy. Both me and my cat really love this subject because algorithms are fun.
Algorithms are fun!
FOA, show the way. Let's go, let's go.
Good morning, everyone, and welcome to Foundations of Algorithms. We are so excited to have you here. You can see I'm literally shaking with excitement. For those of you who are new at the University of Melbourne, again, also welcome to the university and welcome to the semester. I know it's only been 3 days, but hopefully you're already getting excited with some new friends, new things to do, and of course, new classes. So to kick things off, I'm going to give you a little bit about this adventure that we're all going to be going on for the next 12 weeks. So in this class, we have, as of yesterday, more than 400 students. And while if you look around you, some of them are over there online, hello online students, we still do have a good few hundred of us here. And we're from all across the university. We're not just Bachelor of Science students, not just computing major students. In fact, when I went to check earlier this morning, I found 6 degree programs represented. So hands up if you're Bachelor of Commerce. Bachelor of Commerce, we've got a couple of you, Ethan and Max. Already doing okay there, we've got some familiar faces. Okay, Bachelor of Science students. Do we have any Bachelor of Music students here today? No one? Okay, other degree programs, what am I missing? Design, oh, Bachelor of Design, hands up Bachelor of Design. Okay, we've got a few of you in the house. Wonderful, and we also do have students coming on exchange from other places, and so take the time throughout the semester to meet some of the cohort and get to know people who might be studying something a little different to you. We, of course, also have our 10 beautiful teaching fellows, some of whom are with us today. Teaching fellows, if you want to stand up. And we will give you the microphone and a chance to introduce yourselves just quickly. It'll turn on in a second. You just have to wait. There we go. It's green.
Okay, hi, I'm Casey. I'm the head TF for this semester. So, hello, welcome. We really enjoy the subject. It's a really great subject. Having a foundation in C programming really gives you the ability to transition to basically any programming language since it's starting point for a lot of things. So, I really hope you enjoy it.
Hi, my name's Patrick, and I agree with everything Casey said.
Hey guys, I'm Tracy. I'm the one with the cat. Her name is Nano. She wanted to come this morning, but I said no because she woke me up 6 a.m. And I agree with everything Patrick and Casey have said.
We also have 3 first-year fellows who you will meet in the first-year center. Hands up if you've been to the first-year center before, if you've taken FOC with us. A couple of people have been to the first year center. I see some regulars among the crowd. So this is a place where every day of semester, starting from week 2, you will be able to drop in and get daily support with whatever is frustrating you. Whether it's a coding exercise, whether it's something conceptual, our first year fellows are going to be there to support you. We also have one full-time production associate over there. Give everyone, give Rithik a small round of applause. He's making all of this stuff happen. And this year, we're also expanding our team with some production assistants. So if you're involved in production assistants this morning, stand up, give us a wave. Stand up. And you'll be seeing more of our production team throughout the semester. Then, of course, we have our 3 subject coordinators. So what would this class be without our Associate Professor Zhang Zhang?
My name is Zhang Zhang. I'm an academic within the School of Computing Information Systems. I've been teaching this subject. I was just counting my fingers, the 10th version now. You'll be seeing me more in the second half of the semester, where I handle the assessment tasks and also teach a couple lectures, a couple of weeks of lectures. With that, I guess I'll pass back to Shannon.
And unfortunately, Dr. Sasha Sarain, who's also one of the subject coordinators, could not be with us here this morning, as she is running a board games conference, which is actually super exciting, but she'll drop in on us at some point later this morning once she's done with the keynote.
And as you'll see in the coming weeks, as you write your own code and solve your own problems, what ultimately matters in this course is not so much where you end up relative to your classmates, but where you end up relative to yourself when you began. And it really is all about that delta, whether you've programmed or not, just getting something out of a class like this. And if it does take time, and if you do feel those frustrations, but you simultaneously eventually feel that sense of accomplishment, that just means it's all working. And indeed, hopefully, all the more worthwhile and gratifying ultimately as a result.
So that is Professor David Malin, who teaches a class called CS50 at Harvard. Hands up if you've heard of CS50 before. See at least a bunch of people. So you may have gotten that some of the vibe here is a little bit the same. And that is in fact because sometimes I teach CS50. And so we're going to derive some of our teaching methodologies, the way we teach the class, but not the content from CS50 itself. In addition, in the first couple of lectures, you might see a couple slides with a duck on it. Those slides are shamelessly borrowed from CS50 and adapted for our own context. But all that said, Professor Malin's message here is really important. What it really matters for the class is not do you come in knowing how to be an elite coder and do you come out ruling the world like, I don't know, the next Zuckerberg. What matters is the delta, the difference between where you are today and where you finish at the end of semester. As long as you have grown substantially, as long as you put in time and learn something, I think mission accomplished. Now, of course, we'd all like to get straight H1s, but I was not a straight H1 student, and so I certainly don't expect it of you. What I expect is a commitment to learning, showing up, coming to tutorials, being an active and engaged member of this community, and then we will all achieve what I consider to really be success. So with that, let's talk a bit about the reason we're all here. We're here to talk about algorithms. And algorithmics as a field is really about the art of solving problems. Now, I say art and not a science. Does anyone have a sense of why this might be? Why would we consider algorithms to be an art rather than just a science? Okay, remind me your name. We had a chat about hacking last semester.
I think that algorithms is a way to solve a problem.
It is a way to solve a problem, but what about solving a problem makes it not just a science, but also a bit of an art?
I have no idea.
Okay, do you want to pass the microphone? Let's get it back a couple rows. Quick, quick, quick. See a hand up over there.
There's more than one way of getting it done, and so the creative aspect of picking and choosing your solution is what makes it an art.
Yeah, so there's something about figuring out what are the relevant aspects of a problem, being creative, trying to tease apart the relevant aspects of the problem that are specific to what you're trying to do. It's not like there is a singular correct answer for every single problem out there in the world. How you specify the problem is going to determine the kind of answer you come up with, and also you can use pieces from all different things you've learned from FOC already, or from your programming experience, or from what we learn in this class and future classes, in order to construct a solution that might be somewhat novel and different. So you have all seen this kind of black box model of a computer before, but specifically when we're thinking of algorithms, it's this process in the middle here, this process of taking some input, doing something to it, and producing output at the end according to a defined specification of what we want to achieve, some kind of transformation on the data. Now you can imagine all kinds of different problems that this would apply to, not just ones that might typically scream algorithm in your mind. Who has something in mind where there's input data and something that you output? It can be from ordinary life. Think about maybe your experience as a student early this semester, before you even stepped foot in class. Where would an algorithm have been involved? Some transformation of data. Okay, let's pass the microphone forward and I'll keep one on back up here.
I have a micro. Pardon? I have like a algorithm, I guess. You can say that picking what courses you're gonna choose out of all the courses, that could be an algorithm.
And what makes that difficult?
You have to weigh what content you're going to be taught, and then you're going to weigh what you want to do, and a few other stuff. I'm not quite sure, but just think about it.
There's a big one that's time-related. What's the time-related piece of that? With picking what classes you're going to do?
The availability is on like semester 1, semester 2, summer or winter.
Availability and scheduling. In fact, scheduling is an entire area of algorithms research. Just the kinds of things that you do as a human to figure out, okay, how am I going to make my courses fit, is something that people have dedicated decades of their life to figuring out how to do that efficiently using a computer. Now, of course, for your own classes, you can like pick and choose and try it a bunch of different ways and see what works, and that's somewhat effective. But imagine you're scaling up to a big business or to the whole university and trying to figure out which classes go in which room at which time. That immediately becomes a problem which you can't just kind of try every different combination. We need something a little better, a computational way of doing that. So that can be one of our very first algorithms. What about someone have another idea for an algorithm that you may have experienced somewhere in life? Let's get this one over to you.
I got it. We sat all of our exams and then we got given study scores that became ATARs.
So there is an algorithm involved in converting your high school exam scores into an ATAR. It involves some amount of statistics, but there's some computational process running in there, collating all the data and figuring out how to turn the input data, the raw input data, into an ATAR ranking for all students in Australia. What was your name?
Lottie.
Lottie, thank you. So what we have in this black box here, and the focus of our entire semester, is going to be algorithms. Now, of course, in order to study algorithms, one of the very useful things we can do is actually to build them. Now, an algorithm exists regardless of whether you've written some computer code to do it. In fact, like we were talking about, what was your name over there who had the scheduling problem? What was your name who had the scheduling problem? Ronald. Yeah, as Ronald was telling us, not some algorithms we just do as people. They don't even need to be written down. They don't need to be put in code. The idea of an algorithm is separate from the implementation of an algorithm. The implementation which is what we will spend part of our semester on, implementing the algorithms in C, but a lot of our focus will be on the analysis and design of algorithms, which is something you don't actually even need a computer for. It's enough to have a fairly expansive brain or otherwise just a pen and paper. So one of the other concepts that is going to be relevant to us is infinity. Now, unfortunately, as much as I would love to spend all day talking about infinity, it's going to be particularly relevant to us in the study of algorithms because of a fact about the universe. What is the universe fundamentally? Finite. The universe is finite, and so we're not going to be able to tackle problems of infinite size. We're not going to be able to tackle problems that take infinite memory. We're not going to be able to tackle problems that take infinite time. In fact, my research area, cryptography, is built around this idea that maybe we can come up with problems that are so difficult for computers to solve that even if you set all the computers in the universe running on them, they wouldn't be able to break the code in the amount of time left before the universe crunches in a fiery crunch or expands out so that the entropy of the universe is effectively infinite. But coming back from those kind of like heady philosophy ideas, Algorithms is also about these things. Now, has anyone seen one of these old Macs? What's the oldest computer you've seen? Lottie's seen one of these. Okay, what is the old, let's get someone else in the audience. What is the oldest computer you have seen and what did it look like?
Maybe similar to this.
Similar to that? At the first year center.
They have that model.
Outside the first year center, there is a door that says computing lab, and behind it is a really, really old computer. Now I will show that picture for you for just a second. There we go. So this is actually one of the oldest computers in the world. This is CIRAC, which was actually at the University of Melbourne. And so when you wander through Melbourne Connect, you might see a number of photos and a number of references. So this was back in the days when computers would even take up the size of an entire city block. Thankfully now, all of us have powerful computers in our pockets. And these are also capable of running algorithms that are far more powerful than any of these older computers that we were looking at. Okay, so all well and good. We've talked a bit about what an actual practical computer looks like. We've talked about this notion of an infinite computer. But now let's choose a concrete problem and think about that problem as a way to launch ourselves into the world of algorithms a little better and actually understand why this might be difficult, why this might be interesting. Right now, it's all pretty up there and abstract.
In post-World War I Europe, secrecy between paranoid nations becomes paramount. The growth of international commerce creates a need for companies to keep their information secret from competitors. Germany's Arthur Scherbius develops the Enigma machine as a means of keeping those business transactions secure. It works by generating an electric current when a letter key is pressed. A number of moving mechanical parts then scramble the path of the current, producing a different letter each time the key is pressed. The Enigma machine is about to become the German Army's most powerful code-making weapon in World War II.
So, once again, the world is in a time of geopolitical tension, so hopefully that means my job as a cryptographer is in good supply. We'll need codes and ciphers. But as in this particular historical example, one thing that is kind of key to signals intelligence, or this idea of code breaking, is looking for patterns in larger bodies, or in this case, larger bodies of text. Now, in programming world, we're often going to refer to letters and numbers and symbols as strings. That's just a fancy term of saying like a collection of letters, numbers, and symbols. So in this string, our problem for the next 45 minutes or so is going to be to find all repeated strings of larger than a certain length. Because if you find repetition, that's a sign of something complex, of some structure that's going on. And maybe using the structure, we can actually use that to break a code. Now, of course, this code is from the 1930s and 40s, so I would not recommend enciphering your messages today with an Enigma machine. As well, they're kind of hard to come by, although there is one in the city of Melbourne right now for a gallery exhibit. But this leads itself to a concrete algorithms problem that we can then talk about. So let's frame it a little more formally, not in math language, but at least enough so that we can start to get a grasp of the problem. So let's phrase it as follows. How can we efficiently find all places in the string or the message where there is a repeated subsequence of at least L characters? Now, L is not special here, it's just a variable. We could call it N, we could call it M, and you'll see throughout this that we will we may vary the variable names depending on the specific problem that we are looking at. So here's an example of a string. fat.rat.eat.bat.cat.eat.fat.rat. This is, Trace is gone, but this is one of Nano's favorite parts of the class because she enjoys chasing rats. So let's switch over to a demo with the string. And I'm going to run a program, find repeat 0, and I'm going to put some, oh, there's Trace. I'm going to put some text, feed some text into it. I'm going to run a command on the computer. We'll see how to do this shortly. And our goal is to find all the repeated subsequences of at least 7 characters in length in here. So I'm going to switch over now. So the first thing I'm going to do is actually take my program and run some set of commands that will enable me to actually execute it. So don't worry about these for the time being, but we will get there. Actually, I said we were going to do find repeats 0, so let's run find repeats 0. There we go. And let's create a text file that has fat.rat. It's got the text that we want in there. So that's test1.txt. So now I'm going to run, just like we saw on the slide, find repeats 0, looking for repeats of at least 7 in length, was test1.txt. There we go, we can see we got exactly the same output. In this case, n is going to be the length of the overall string, the length of the message in which we're looking. M is going to be the size of the repeat that we're looking for. So we're looking for repeats of exactly 7 letters, 7 characters long. And then we can see that there were 3 of them. One started at position 0. One of the repeats started at position 1. And one of the repeats started at position 5, and there were 3 of them. That explains all the output there. Now, one other thing I can do is I can add the time command out the front here, and then it will tell me how long it took. Now, the number is so small here that these numbers are all effectively 0. Running it, our algorithm, our very first algorithm, on this text with a repeat of 7 took pretty much no time at all. So that's not so interesting. I mean, okay. So now let me try it on a bit of text that's much, much bigger. So I have a copy of all of War and Peace, and I'm going to run it again. Okay, this algorithm is not so fast now. And I mean, maybe it's because I'm looking for repeats of 7 letters, and there are going to be lots of repeats of 7 letters long in War and Peace, right? Okay, so let's try something a bit larger. Try 25 letters. Oh. That's going to take an awfully long time. So let's call our find repeats 0 is certainly an imperfect algorithm. But I am going to show you what the algorithm looks like, and then we can analyze it to figure out why it might not be the best way of solving this problem. It's fine for when we had our tiny test string, the fat.rat, but it's not so good when we have something longer. So here's the algorithm that is behind find repeat 0. And we're not going to worry about the computer code part of it for the minute. We're just going to focus on the algorithm itself. It is the following procedure. So firstly, read in the sequence, read in the string, read in the message, whatever you want to call it. Then repeat the following things. So for every value of I, where I can range between 0 and n minus m, do the following. Okay, every one of those. Now, for every possible value of j, starting at whatever I currently is, plus 1, all the way up to n minus m, then compare all the characters in that range between starting at the ith character in the string and the jth character in the string. If all m characters are the same, so once you finish that loop, write an output line. So if all m characters are the same, that means the 2 places that we're looking at the message have matched at each of those indexes, and so we have an overall match for the substring. Now, just saying that out loud is kind of tricky. Most of you probably didn't quite follow what was going on in that textual explanation. So what we do when we get given an algorithm like this is we try and work out, generally with a pen and paper, exactly what it's doing. Perhaps we do a demo on a piece of text we know and try and figure out actually what's going on here. And throughout the semester, as you're trying to understand algorithms, this process of, okay, first taking a look at it, taking a read of it, but then actually going and seeing how it behaves on an example, and then writing the code for it, and then testing the code on real data is going to be the process that actually helps you to understand the algorithms. So here I have my handy iPad prepared, and we are going to follow this algorithm step by step and actually see how it works. So over here, I have our algorithm, and over there up the top, I have our string. So let's clean the slate a little bit and start afresh. So read the sequence S. Okay, that part's not super interesting. Now for I equals 0, so this is position 0 because in computer science we like to count from 0 rather than 1. So that's 0, 1, 2, 3, etc., etc. So start at I equals 0 and go all the way to n minus m. So in this case, m was 7 and n was 23, was it? Was that how many letters were in the string? 32, sorry. 32 characters in this string, so 32 minus 7. Folks, 32 minus 7? 25. So 1, 2, 3, 4, 5, 6, 7. That's going to take us to over here. So I is going to range between all of these values up until this point. Okay, now for j equals I plus 1, so let's start a j somewhere. I'll make this a little bit thicker. So our j is going to start over here at I plus 1 to n minus m, so it's going to go all the way to that point. Compare m characters starting at si and sj. So we are going to compare those two. If all m characters are the same, then write an output line. So we have to compare m characters starting at si and sj, which means we are going to need to move I and j along m times, and check if they are the same. And this is going to be a little tricky to do on the iPad, but you can see we're going to move, let me move j along another one, and I along another one. So we are going to compare F and A, and then we're going to compare A and T, and then T and dot, and then dot and R. It doesn't seem particularly efficient. Okay, let's skip partway through the algorithm to something that will make a little more sense. So let's skip to the point where I is still 0. So I is still here, but j is now 21, which is over here. Okay, so if I were to now compare m characters, what would I see? I would see F matches F. Okay, let's compare the next character. A matches A, T matches T, dot matches dot, R matches R, A matches A, T matches T. So all m characters were the same, so write an output line. Okay, so we're getting kind of the start of what's going on here. So for every possible pair of positions for I and for j, check if you go m characters forward if all of those characters match. Now, why does it make no sense to start I in this part of the string? So, got one hand up. This is going to be a tricky name. Nope, I've lost it. What was your name again?
Tim.
Tim. Okay, Tim, why does it make no sense for I to start at this part?
Well, we've specified that m, which is the length of a sequence, is 7. So if it starts, say it starts at the A in the last fat, then it can't possibly be of length 7 because there's not even 7 characters left to check.
Exactly.
So we know it's wrong.
So let's say I had I over here, and we're looking for m characters. Well, we hit the end of the string, so there can't possibly be a repeat of 7 characters when there are only 6 characters left to look at. So we know that we should at least start I such that there are 7 characters left. 1, 2, 3, 4, 5, 6, 7. Oh, I was off by 1 in the drawing. Okay, let's clean that up. Okay, someone else, what is bothering me about this algorithm? What seemed really inefficient? Have we already heard from you? No, okay, and I didn't catch your name either.
Alex.
Alex.
It's fine, I'm new to the school. And
what's so annoying about this algorithm?
It theoretically steps with every letter within the string to the square.
Okay, I'll need you to explain it a little more clearly for me. You were right,
yeah.
But I want you to explain it again.
So there are 2 loops. One loop loops so I just steps to every single string until the last 7. And then there is another loop that does the same thing. So theoretically it loops to the big O of square.
So we don't know what big O is yet, so that's not going to be helpful. Yeah. But you're getting something. It feels like we're doing a little too much work. So let's do another example where I'm going to put J over here. So J is 0, 1, 2, 3, 4, 5, 6, 7, 8. And now we're going to check m characters, so we're going to check 7 characters to see if there is a possible repeat between what starts at 0 and what starts at 8. Okay, so we check, does F and E match? Does A and A match? Does T and T match? Does dot and dot match? Does R and B match? Does A and A match? 2, 3, 4, 5, 6. And so we want to check, does T and T match? Why was I wasting my time? What's wrong with this process? Okay, Darcy, you can take it from Alex. Or Lottie.
The main problem is you check that F and E match and they don't. And then you go and check all of the others.
Yeah, so why am I bothering to check all of the letters when as soon as I've checked the first letter, I already know that this isn't a match? So I'm wasting a lot of my energy. Okay, so we've identified a problem, we've identified how it works, but now we probably want to describe how long this procedure is going to take. So this is where, as Alex said, we will later in the class use something called big O notation. Ooh. Uh-oh. And the undo button is not working. Okay, we are going to jump to this, where I have thankfully a backup slide. I'm going to make that a little bigger, and we'll do our analysis here. There we go. Okay, so how many possible values can I take on? Someone else? It was Tim. No? Tom. And where's my Tim? Tim's there. This was a problem last semester. Okay, Tom. How many possible values can I take on?
In this situation, it's 0 to 25, so is it 26?
Yeah, so this is going to take us from 0 to 26, but let's actually parameterize it. It can take on n minus m values. Now, let's imagine we're working with a big piece of text. So n is going to be much larger than m. M is the length of the repeat, n is the size of the thing that we're searching in. And because n is much bigger than m, we can probably just ignore the m for some of our analysis. Okay, so I takes on n values, and for every value of I, we're also going to do that in a loop. We're going to do those steps for checking every value of j. So for every value of I, we are going to do it once, we're going to do the following steps for every value of j. Now, how many values can j take on? Did I see Isabel? No? Or was it, what was your name again? Charlotte? No. Forgotten, yeah. Elizabeth. It was close with Isabel, but not quite there.
In this case, you're ranging from like I equals 0 plus 1, so 1, or whatever I is at the time, to n minus.
Good morning.
Good morning. I'm not sure where that came from, honestly. That was kind of interesting.
So for like a really massive text file, like that's a pretty big range as well, depending on where your I is.
So it's not... Go ahead. I heard someone else say something? No? Okay, so it's going to go up to the full length of the text again, but each time it's going to be one less as we go along. So we can say that it will be, in the worst case, it'll be another n letters. Now, we will get more sophisticated as we go along and figure out how to deal with the fact that it's going to get smaller and smaller and smaller. And to do that, we can use some of the mathematical techniques you'll be learning if you're taking maths classes about series. So it would be like 26 plus 25 letters, and then 24 letters, and then 23, et cetera, et cetera. But we will handle that analysis later. So n by n, and then what's happening here? How much work do we do for each of these steps? How many comparisons do we do? How many letters do we have to compare? It says it right there. M. So this is going to run once for every possible pair of positions. And so that's another way of doing this analysis, is to figure out how many pairs of positions there are. How many pairs of positions, and then for each pair of positions, it is going to run m comparisons, m character comparisons. And so this gets us, if we total that up, n squared m worst case. Pretty bad. Okay, now we are going to do a very brief interlude for a special guest. Can we have a drum roll? And Dr. Sasha Serene, if you want to come to the front. And, we have a microphone.
Hello, everyone. Sorry I'm late.
Want to tell everyone what you were doing?
Yeah, I am running a conference right now at Melbourne Connect on our research on an international conference on games. So right now I had a panel that I was chairing for people from here, Canada, and most of Europe. And that ran a little bit long, so I apologize for interrupting your lecture at the moment.
And Sasha is going to be with you for next week and the week after, taking us through some really exciting material and helping you gear up for some more complex algorithms later in semester. So a short round of applause for Dr. Sasha Serene.
All of you next week.
There we go. Oh, that was Siri. That's what it was. AI is getting too good these days. Okay, so our find repeats 0 worked all right, and it did run for our smaller string. But for bigger strings, we ran into substantial issues. We saw that computer over there just kept running and running, and it didn't manage to solve the problem for War and Peace. So the question we wanted to ask when we did our analysis was, how much extra work do we have to do as the size of our input gets bigger? Now, we can think about that in two ways. We can think about both the amount of time that it takes, the number of extra steps that the algorithm has to do, and we can also think about how much extra space in the computer's memory the algorithm has to take up. So maybe it's keeping track of something as it goes along. How much extra information does it have to keep track of as it goes through the algorithm? So the way we think about it is roughly this. For every n units of growth in the size of the input, so if I make the input bigger by n, by what proportion does the time needed to run the algorithm grow, or does the memory needed to run the algorithm grow? So for example, if my algorithm is whatever input you give me, I spit back the number 1, how long does that take to run? How many steps? Hold up on your hands. How many steps does it take to run? I should see a lot more fingers. How many steps does that algorithm take to run? 1 step. Whatever input you give me, I give you something immediately back and don't do any work. So that algorithm, as n grows, that algorithm doesn't really grow at all. It doesn't take any more work. No matter how big the input gets, it still takes the same amount of work to run the algorithm. So it doesn't really matter if it was exactly 1 step or 10 steps or 100 steps. What doesn't change is the proportion between the size of the input and the amount of time our algorithm takes. This is in contrast to our find repeats algorithm, which as the size of the input grew, let's say as the size of the text we were searching in grew, it would take a squared amount of time in proportion to the growth in the input. So that's pretty significant. And this is where we begin to talk about what Alex mentioned for us very briefly, big O notation. And this is essentially a way of saying, okay, let's throw out all the things that don't matter. So it didn't matter when I was just talking now if it took 1 step or 10 steps or 100 steps. What we cared about was that proportional behavior. The fact that no matter how big the input grew, the time that the output take didn't change. Or the fact that when we grew our input by n, our output time would be proportional by a factor of n squared. And big O notation essentially allows us to throw out all the additional information that we don't care about. We don't care exactly how many steps the computer takes. We don't care if it took 5 seconds or 6 seconds. What we care about is the relationship between the size of the input and the overall pattern of how long it's going to take. So we can draw a graph like this, thanks to our friends at CS50 for providing the slide, where on one axis we have the amount of time it takes to solve a problem, and then on the other axis we have the size of the problem. So how big our piece of text is, how many students we have to schedule, how many boxes we have to try and pack into a space. So a pretty good runtime is that for every unit of extra information that we've given the algorithm, it should take an extra unit of time to run. Now, an extra unit of time to run could be 10 steps, it could be 100 steps, but what matters is whatever unit size you pick, for every additional input unit, you're going to keep the same number of additional steps. We could go even better than n, and we could say, well, if I give you n units of new information for your algorithm, you are only going to have to do n on 2 units of additional work. But given that I didn't care about the specific number of steps, that was of which an additional unit of work was composed of, why might I not care about this distinction between n and n on 2? So I need someone new. Okay, let's get a microphone back there. And I've forgotten your name as well.
Ella.
Ella.
Yeah, because they're both linear.
They're both linear, they both have the same proportional behavior, and it's the difference between saying, okay, 1 unit is 50 computer steps versus 1 unit is 100 computer steps. They're kind of interchangeable. What we care about here is the overall behavior. So when I run it on a physical computer, there is a difference between n and n on 2. For the purpose of analyzing the behavior of the algorithm, we don't want to take into account the specific things of like, how many particular steps does this computer take in order to do an addition? Or what is the speed of the processor? We want to throw all of that extra information away and just ask ourselves about the behavior of the algorithm overall. So we can see that for this particular example, for the same size of problem, the amount of time to solve is going to be less for the n on 2 than it will be for the n. And we can do this chart with a whole range of different functions that we're just going to pick out of our mathematical toolbox. But it turns out in our analysis of algorithms that some of these, what we call runtimes, the amount of proportional growth you get is going to follow often a few different patterns. So a linear runtime, or a runtime of big O of n, that's just the way we say it, big O of n. So a linear runtime is pretty common. A runtime that grows logarithmically is also pretty common. And you'll see things like polynomial runtimes as well that are like n squared, n cubed. And it's fairly uncommon that you'll see something really weird and exotic that has some strange function. Most of the algorithms we're going to study in this class at least will be either polynomial runtime, so big O of n squared, logarithmic runtime, so big O of log n, or linear runtime, big O of n, and with some slight variations on those, and we'll throw in a couple more parameters as we go and show you how they impact the big O behavior. So our first algorithm was slow because of what I think Alex pointed out, right? You pointed out the issue we were having. It was this bit in the middle where we had the doubled up loop that was really causing us trouble. This algorithm is taking n by m, giving us a big O of, just say it out loud, big O of n squared m for this algorithm. So not very good. Now, if I were to dive into this a little deeper and actually check inside my computer what is actually happening, what particular circuitry is being invoked by the computer to run this comparison, I'd see something that looks like this. Now, you don't have to worry about it. This is in a language that the computer deep down uses to run instructions called assembly. And I looked at the loop and counted how many instructions it actually took to do each comparison. So we said it took n by n, that's how many different possible starting places there were, and m comparisons, and then each comparison is going to run 10 of these machine instructions. So if we wanted to be super accurate for this particular computer, we could say it's going to run in 10 n squared m. But as I said before, adding that 10 isn't very useful. Why is that not useful? Ella, you've still got the microphone? No, it's disappeared. Okay, we've got someone in the middle over there.
Because the number of steps the computer takes will depend on the architecture.
Yeah, it's going to depend on the particular type of computer I have and the exact specifications of the program I built, but we don't care about all of those details for the purpose of analyzing the algorithm itself. All we care about is, again, this proportional growth factor. So, but let's, for the sake of argument, actually run the calculation and analyze the algorithm for my real machine. So where n is 1,000 and m equals 10, I've just chosen some example numbers, then n squared by m equals 10 to the 7. Multiply that by 10 again for the number of instructions per comparison, and then I get 10 to the 8. My laptop, or at least this laptop, does about 10 to the 10 operations per second, so runs one of those like mini instructions that I showed you. So let's do the math. 10 to the 8 on 10 to the 10 equals 1/10,000th of a second for these parameters. So n equals 1,000, m equals 10. So I'm going to set that up with, what did I say? I wanted m to be equal to 10, and I know you can't see this yet, and n equals 1,000. So I'm going to find repeats with m equals 10 and n equals 1,000, and it takes about 1,000th of a second. You can see I got the 0.01 there, but that's really kind of a trick. This timing isn't accurate because the numbers are too small. But when n equals 1,000,000 and m equals 100, then n squared m is 10 to the 14, do the math, 10 to the 14 on 10 to the 15 for accounting for the fact that there are 10 instructions for a single comparison. Divide that by 10 to the 10, that gives us almost 30 hours. So let's give it a try. Does anyone have anything on tonight? Tomorrow? Okay, let's do 2, 3, 4, 5, 6 zeros for 1,000,000. M equals 100. Well, that's not making much progress, is it? We'll leave it there and we will come back tomorrow, I guess, or the day after and see what progress it's made. Okay, so anyone here heard of Moore's Law? Can someone give me a quick version? Just shout out, what is Moore's Law over there? So as time goes on, we get more transistors packed into a given area of silicon, which, I mean, if we assume a loose relationship between the density of transistors and the speed of our processors, we should get a relationship between as time goes on and our processors become more dense, they should speed up. And for a long time, all the way from the 60s up until around 2010, we saw a doubling of processor speeds roughly every 18 months. Now let's run the microphone. Still over there, and I had to get your name.
Ankit.
Ankit. So what is the problem?
It's like you can only pack, especially if say one type of transistor is a finite amount, you'll eventually reach a maximum. It doesn't just grow infinitely, especially if it's
Firstly, as a matter of physics, there's only so much stuff you can pack into a given amount of space before what happens? Trace, you can answer that one. What happens if you pack too much space? Tracy? What happens if you pack too much matter into too small a space?
Well, it don't fit, right?
What happens if you keep doing it? You keep putting energy in to pack things smaller and smaller.
Well, you get weird quantum effects.
And if you do it enough?
Then you get really weird quantum effects and things start not behaving properly.
You can get a black hole, right?
Yeah.
So essentially, we are limited in the speed of our processors because we're trying not to create black holes in this class. But what this means more practically is that not only are there physical limits, but there are also engineering limits to how many transistors we can pack into a given area of a silicon chip. There's a limit to this pattern of doubling of transistor speed every 18 months. And indeed, in the last 10 or so years, we've found that this pattern is now broken. Which means that just relying on better and faster computer chips to make this run faster is probably not a viable solution. In fact, what we need to do is come up with better algorithms. So even with Moore's Law, we would have to wait 20 years, assuming that Moore's Law was still functioning, for this other program to finish in a reasonable time. So probably not the best bet. In 20 years' time. So instead, we can follow Alex's suggestion. And instead of checking all m characters every time, we can instead stop. When should we stop checking characters? Let's give it back to Ankit because he's right there.
We could stop when for one pattern.
As soon as you find the first character that doesn't match between your parent string, or the string in which you're checking for repeats, and the substring, you stop. If F and E don't match, there's no need to check if A and A match, because you already know that these two strings are going to be different. So, on average, assuming that our string is composed of a random selection of letters, now English is not random, but let's assume just for argument's sake that it is random. On average, how many comparisons will you have to make before stopping? It's how many characters will you have to check before you stop. So what's the probability of two characters matching?
26 or 52.
So the first one doesn't matter, whatever it was, and then there's a 1 in 26 chance that the second one you picked is the same thing.
Yes.
So 1 in 26, which means that normally, will you proceed on ahead to check the second one?
Yes.
Why would you check the second one? The first one didn't match. You only had a 1 in 26 that matching, right? So what do you expect to happen 25 out of 26 times?
You can skip the first one.
Well, we know if the first one doesn't match, that the rest of the thing is not worth checking, because what we want to know is does every single possible character up to m along match? So normally, how many comparisons will we have to do before stopping? One. Because all you do is check the first letter in the string at position I and check the first one at position J. and they're probably not going to match, which means you're not going to have to do all M comparisons. Now, thinking back, let's go to our runtime. So we said the prior algorithm was going to take, leave it there. What was your name again? Liam. So we previously said we're going to have to do, there are n by n places that we're going to check, like combinations of starting positions, and we're going to do n comparisons. So in our improved algorithm, what's going to change about this? So on average, you said would do one check.
Yep.
So how would I modify this? This was if I didn't do that stopping behavior, if I always checked all m characters.
Mm-hmm.
So how would I modify that runtime?
I mean, you could index the first character for m.
This is more an analysis question of how many steps do I have to do? Do I still have to do n by m?
Right. No.
So it's n by n by...
Oh, I'm not quite sure.
Just by one.
By one.
Because you said most of the time we're only going to have to do one step.
Right.
So on average, this is just going to be n by n. Thank you very much. Round of applause for Liam.
Hey.
Now, I'm still not particularly happy. So now I have a runtime of n squared. Why does that not... let's get here. Here's our new algorithm. This one now has a runtime of average case n squared. Why am I still like a bit unhappy?
As n increases, the time it would take for the algorithm to run would increase exponentially.
Not exponentially, it's still polynomial, so it's still n squared. But n squared was the whole problem we were having. That factor of m wasn't really the big deal. M was always a small number, so we were looking for like m equals 25, m equals 7, m equals 100. The big number was the n, the size of the thing we were searching in. So even though we've improved our algorithm a little bit, it's still not going to be that much better. So let's go and actually try it out over here. And switch to find repeats 1. And I'll tell you that find repeats 1 implements this, actually I will recompile, and we'll talk about that later today. Recompile find repeats 1 just to make sure it's right. And I'm going to run it. And it's still not doing very much. And if you don't believe me that this program actually works, let's just make this smaller and make that smaller. And you can see that the program actually does work. The problem is that we've still got n squared behavior. So it's much faster, like we've changed that behavior so we don't have to do m steps every time, but that hasn't solved our overall problem. Worst case is still n squared m in the worst case, but we know based on the statistical patterns of English, which isn't 1 in 26 every time, but it's not bad, that we're still going to have done considerably better. So let's say for English, we're going to check on average the first K letters, knowing that many words in English start with, for example, TH. So the chance of us comparing TH or THE is going to be better than just checking, okay, let me scratch that. The chance of us encountering the start of two subsequences that match in English is a little higher. So K is not going to be 1, but it's also not going to be M. So it's faster, but not fast enough. When n equals 1,000,000, we still need to do at least 10 to the 12 comparisons, and so that's at least 1,000 seconds. 1,000 seconds is a lot better than 20 years. It's a lot better than 20 years. It's still not good enough. And this is what computer science is all about, this kind of idea. Figuring out this mix between the practical bit, thinking about what's actually going to run on my computer, the bit of analyzing the algorithm in the totally abstract sense, in the mathematical sense, the part of the problem where we thought a minute for how English language factors in, so the actual data that we'll be running it on, as opposed to truly random data, and combining all of these different pieces into an understanding of the overall landscape of the algorithm, the overall design. This is what computer science is about, and this is what we are going to be spending the next 12 weeks on. The basic idea here is you can do either a bit of work ahead of time or store some information on the side in order to make your life easier when it actually comes to running an algorithm. And the way we're going to do this frequently is using something called a data structure. Now, a data structure is not a physical thing. It's an abstraction. It's an idea. It is a way of arranging data, at least in an abstract sense, that's going to make it easier for us to access, recall, and use that data later. A data structure fundamentally is just describing the structure of the relationship between different pieces of information. Now, if any of you have seen your parents' old tax filing closets, anyone have seen their parents' tax filing closets? Or paperwork at home, bills, stuff like that? Depending on how good your parents are at organizing things, it might take them vastly different amounts of time to search for their old product warranties, their old tax files, their old bills. If they've got a filing cabinet, just like you have on your computer, files and folders, there might be a more efficient way to access the piece of paper they're looking for than exhaustively going through every piece of paper in the house. In fact, what my mum does is in her filing cabinet, she has everything categorized alphabetically. So for example, the bicycle warranty will be under B for bicycle. The taxes will be under T for tax. And so instead of her exhaustively going through every piece of paper, let's say there are N pieces of paper, how long would it take to look through every piece of paper to search for something? If there are N pieces of paper and it takes 1 step to look at each piece? N steps. Okay, so that's bad. But instead, if she's opening the filing cabinet and going to B for bicycle, it's pretty much instant. She knows she can go right to the letter B, and then if there are a few pieces of paper in there, she might have to do a small number of looks at the paper to see, but it's much, much faster. And you can do the same thing with computers, not just with this kind of filing cabinet idea, but with this whole notion of arranging data to make it easier and faster for you to access things and then for you to perform certain operations. Now, one of the big challenges in the design of algorithms is to figure out 2 things. Both the design of the data and the design of the algorithm that matches. The 2 kind of go hand in hand. If you can figure out a clever way to organize your data such that it can be taken advantage of by the computer, you can often get very, very substantial performance increases in your algorithms. And this is what we're now going to do with our fat cat rat eat bat demo. So this is an example of a data structure, and it's called a suffix array. And one thing that you will notice about it is it has every possible suffix of our string in it. So starting from fat.rat.eat.bat, whatever, then at position number 2, we have the same string, just without the F. Then at position 3, we have the same string without the F and the A. At position 4, without the F, the A, and the T. And we know by virtue of the way that this table is arranged that every possible suffix is present in it. Now, right now, this data structure actually isn't of much use to us. There's still something we have to do in order to make it useful for our problem of finding all matching substrings of a given length. So using my magic right arrow and my sorting button, I'm going to create a new version of the structure. Now, just looking at it, this is not a particularly deep question. What are some things that you observe about this version of it? It's halfway there.
It's in alphabetical order.
It is alphabetical, but we're going to change the term a little bit because we're in computer science world now. We'll call it lexicographic sorting because we have some characters in there that are not alphabetical. So the full stop, the period symbol we have in there is not part of the alphabet, so we're going to call it lexicographic, like lex, which means word in Latin. So it is in alphabetical order. Can you tell me some other things you can observe about it? What does that mean, the fact that it's in alphabetical order?
It's easier to check if they have the same start because they're kind of grouped together now.
Yeah, that's 100% right. That's really exciting. So we can see that the strings that start the same way are right next to each other in the data structure. So let's see if you can come up with a bit of an algorithm for checking if there are matching substrings in here. So let's say I want to look for matching substrings of length 2. How would you go about doing that if I gave you this data structure? I'll stay with Maka for the minute.
Sorry, could you repeat that?
So let's say we want to do the same thing. We want to find repeats. We want to find them of length 2. How would you use this data structure?
You can add a step checking if each line has at least 2 to begin with.
Okay, so first thing, let's just make sure there are enough letters in it. Okay, let's assume we've done that.
And then since they're kind of grouped together, you can automatically assume that the first one is the same. So you're just checking the second one.
So let's try that. That works for our very first one. So we see A and A on that first line and the second line. So the line that's numbered 30 and the line that's numbered 10, they both start with A. Then what do we do?
You can then loop and repeat.
So we're almost there. I'll help you fill it in. So if we're looking for repeats of length 2, now we can go, we'll check the A's, and now let's check the T's. Okay, they match. So we've actually found a match of length 2. Now what we want to do is we want to see if this at thing is repeated in the next one as well. So we've checked line 30 against line 10. Now we should check line 30 against line 14. Does it match?
Yes.
Okay, we keep doing that all the way up until we get to line 13. What happens at line 13?
The A and the B don't match.
They don't match. Okay, so what should our next step be? Should we move our checker to line 10?
You can go to the next letter because the A and the T in bad. I don't know if that's what you're asking.
So we've already checked line 10, and we know it's going to match with 10. 10 is going to match with 14, 10 will match with 6, 10 will match with 18, because all of them have actually matched with that line 30 at the top. So in fact, it allows us to skip all the way down to where that B line is, line 13. And now we can check line 13 against which one? What's the one that we're going to check line 13 against next?
17.
17. Sorry, yeah, 13 against 17. And does 13 and 17 match?
No.
Okay, so what do we check?
17 and 9.
Yep, does it match?
No.
Okay, what next?
9 and 21.
Does it match? First 2 letters?
I can't really see, but I think so.
It is EA, eat and eat. EA, it matches, great. So now we have our new algorithm. We have lexicographic sorting. We know that all suffixes are present, and we know that the strings most similar to any suffix are on either side of it. And these 3 properties allowed Maka to come up with an algorithm that is way better than the one we did before. The amount of work we have to do now is really minimal in comparison with the work we had to do for find repeats 0 and find repeats 1. So here is a written version of the algorithm that Maka just came up with. So the first thing to do, read in the sequence. Okay, we always do that. Next up, create the suffix array. And the way we're going to do this is just by storing those numbers on the side. So create the suffix array, the unsorted version first, and just store at which index you've started. Now I've chosen here to index from 1 just to make it a little clearer for our demo. And then once you've filled up the table, sort it. So that's our first step. And what I've said here is sort it based on the contents of the string at that position, based on the contents of that suffix. And in fact, the way we're doing it here is we only need to sort based on the first m characters because we know that our repeats are only going to be of that length anyway. Then we have our main loop. And this is exactly what Maka and I just went through, so don't worry about if it's more abstract here, because this was the demo we just did. So starting at the top of the table, for each row in the table, compare the first m character, compare the up to m characters, stopping when you get the first mismatch. If you don't get a mismatch, write the output line, otherwise continue on. And so there is our improved algorithm. So what is the running time? And the hint is sorting k items takes on average k log k.
Basically, we have two parts to this, so they're going to multiply together. First, well, not multiply, add together. So we have the k log k, so that's for the sorting, and so k is just the length of the string, I guess.
Yep.
And then...
So how long are our strings going to be that we have to sort?
M.
M.
So it's
we know that we don't need to include the full suffix, we only need to include up to m letters, because that's the length we're checking for the matches.
So would it be m log k or k log m?
Well, k is just a variable.
Okay,
We're
so it's
replacing the k.
m log n. That's the sorting part, but then we also need to do the checking through, which would be linear, right? Because we're just going through the list each item once. So that would just be... Yeah, so it's just m log m because it's the same, well, it would be the length of the list. So that would be on the order of n?
So we get mn log n overall because we are going to have n strings in the array. At each point, we're going to compare up to m letters, and so we're going to do, m and n are too close. I'm going to have to change the letters next time to make it easier to say. But we are going to have to do our construction of the suffix array, and then we get a piece which is linear. So let's run our overall calculation again. Now let's say n is 1,000,000 and m is 100, so the same thing we were doing before. Let's run out how long this would take. This gives us 4 by 10 to the 9. Remember that each comparison takes 10 operations on my computer, so that gives us 10 to the 10, about 1 second.
Wait, I had a question about the previous one. Can you explain the complexity again, please?
Okay, we will go back.
No, yeah. Why is it what was it, m n log n?
Yeah, so it turns out that the sorting is the biggest
Do you have
part of this.
Okay. Oh, and then the for loop gets ignored?
Sorry?
Does the for loop get ignored as after?
It doesn't get ignored, it's just not important because the thing that's actually taking all the time is the sorting in this case.
Okay.
Once we've done the sorting, we just go through the list once and check from top to bottom, okay, do each of these things with the subsequent ones start with the same thing?
And that's just n, or is it nm? Because nm. Okay, cool. And how is that represented then here?
So if we were doing it fully, we'd do plus nm.
Oh, okay, so it is a plus.
Yeah.
Okay, cool, that's it.
Okay, so let's actually run this code on the computer now. So this is m times n by log n, which is bigger than m times n because log n is going to be bigger than 1. And because this term is going to be the largest one in the equation by quite a lot, we're going to ignore the other part. Make sense? Okay, so now let's run find repeats 2. I'm going to run my mysterious command again to create find repeats 2 and see how long this takes. And what did I say? I said m equals 100 and we want 1,000,000. Ta-da, done. Done sorting. And so that took under a second on this computer, probably a little bit faster than 10 to the 10 operations per second. So we did the exact same thing that was going to take us 20 years, but now we did it under 1 second with the aid of a better data structure and a clever algorithm that took that into account. So this is what it would look like if I used my different methods with different sets of parameters. So here's War and Peace with m equals 25, Wall Street Journal with m equals 250. And then if I set n to 100 million, you can see that we're still going to start running into, if n is 10 million, only method 2 is going to run in a reasonable amount of time. If n is 100 million, only 2 is going to run in a reasonable amount of time. And then if n is 1 billion, which is actually not that unreasonable given the scale, the amount of text on the internet. So if you want to start looking for things in a big sequence of DNA or in a big chunk of text from the internet, then even this algorithm that we've come up with is not going to be that fast anymore. We can still do substantially better though. We're not done with optimizing our algorithm because we might want to run this on larger bodies of text. So if we had a better string sorting algorithm, there is an algorithm that we'll look at a bit later called ternary quicksort. We could maybe get a 50% improvement on the practical amount of time that it took to sort. So if we wanted to sort 10 million words, it would take about 50 seconds, which is actually pretty decent. And this could be done with a few hours of programmer work writing this slightly more complicated sorting algorithm. If we used a better way of creating the sorted suffix array, maybe we could get another 100% improvement again. That doesn't mean reducing our time to 0, that means halving the amount of time. This would take probably a few days of work. Suffix array construction algorithms are actually pretty complicated, and there's something that the guy who wrote the textbook, Professor Alistair Moffat, actually spent a little bit of his career working on. And you can get better algorithmic complexity if you change the way that that construction step happened. So that's where we could get with a few hours of work and then a few days of work. But we can actually still do better. We're not done yet. There's a long way to go to improve an algorithm up to the point where it can't be improved anymore. So remember how I had those 10 comparison instructions that I showed you before? Maybe if you manually wrote those instructions yourself, you could figure out a sequence of instructions that allowed you to cut down 1 or 2 of them, or choose particular instructions that run faster on your computer. So maybe you could cut the runtime in half again. So we've now, I don't know, factor of 4 faster. It's pretty good, right? Pretty good. But we can still do better. Who's got an idea for how we're going to do better? Okay, we've improved the algorithm. We have written some of our own assembly code. What can we still do?
Upgrade the hardware.
Okay, Gabriel, wait for someone else. Not Ben. Someone new. Be creative.
Could we maybe split the amount of data and do it in separate goes?
Yeah, that's actually a really good idea. So we still want to have the same program that we've written, but what we can do is split up the information hopefully some way so that bits of the information will be processed by different, fill in the sentence.
Programs?
Well, not different programs per se. I mean, they might be different programs, but what we want to do is we actually want to split it up into different physical machines. Now, when I say different physical machine, I might mean like 3 different laptops. But do you know something about the way that modern laptop CPUs or modern computer CPUs built? Nothing? So when you go to buy a laptop, have you bought a laptop in the last 5 to 10 years?
Yes.
Right?
Yes.
What's the big ad about the speed? How many... I'm hearing it from the audience.
Yeah.
Didn't hear it? How many cores? So that actually means that inside the actual processor of the computer, there are a whole bunch of independent machines, each of which can run their own instructions. So your idea was actually really good. We're going to split up the data, and we'll have the same program, but the program will split the work across the different cores inside the computer. And so, what was your name again?
Lara.
Lara, thank you very much. So if we take a look, here's an image of what's actually inside a modern CPU. You can see that we've divided it up into, I can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 independent cores inside the computer. And if you write your code just right, you can figure out a way to maybe split up a problem so it can be efficiently run by different parts of the computer all at once. However, unfortunately, the algorithm that we just wrote isn't parallelized. It takes quite a lot of work to write these programs that enable you to split it up efficiently and actually get the computer to do this. We have prepared earlier, however, some fancier versions of our program just to show you what can be done if you implement ternary quicksort and if you now use the time-space trade-off. So let's try method 3 and method 4, and I think this should actually be method 4 here. So let's run find repeats 3 with our faster sorting algorithm. Okay, that's too fast. Let's see if I have a bigger one. There we go, I've got one with one more 0. And then run my find repeats 4. There we go, and you can see that in this one, it's actually broken up the problem in such a way that would actually allow us to parallelize it later if we wanted to. Now, this has been a lot of work on one pretty small and simple problem statement. Can you find, if we remember going back a little bit, I'll put up our problem statement once more. Our problem statement was just this one little line. This was our problem statement. How can we efficiently find all places in a message where there is a repeated subsequence of L characters? And this should give you an idea of not just what you're going to do in this class, because some of the techniques we just spoke about were pretty advanced, but ultimately what the job is of a computer scientist as opposed to a software engineer. A software engineer's job is generally much more about actually doing some programming, but a computer scientist's job is often to think about problems in this sort of way and think about what are the types of changes we could make to change the nature of the problem, to change the nature of the way we are solving it. And with that, you all deserve a pretty chunky break. So let's come back here in at, let's say at 11:45.
I'm designing a machine that will allow us to break every message, every day, instantly. I'm just a mathematician.
Sometimes it is the people who no one imagines anything of, who do the things that no one can imagine.
Welcome back to Foundations of Algorithms. For those of you who don't know, that was a short segment from The Imitation Game, which is a movie that tells the story of Alan Turing, who was one of the creators of the algorithmic and mechanical technique to actually break the Enigma code, this whole cipher that we spent the first half of today talking about. So if you want to learn more about how the German codes were broken during World War II, go watch that movie. It's incredibly enjoyable, and we will talk a little more about Alan Turing and his legacy throughout the rest of the semester. So we're now going to move on to another segment talking about computers and the universe, algorithms in the real world. And here we're going to get our first taste of the C programming language, as well as trying to understand why it's designed the way it is and what that actually means for algorithms. The C programming language, which is the programming language that we're going to use to implement our algorithms this semester, was created in 1969, which is quite a while ago, but it's undergone a number of evolutions since, including most recently in 2023. If you read the textbook, I think the textbook's last update was around 2010, so it is missing some of the newer features in the programming language that have been added since then. And when we talk about the C programming language, C fits most neatly into a paradigm we call a compiled language. This means that once you write your code, you have to run a second program which then converts your code into the assembly language that the computer understands a little more closely, and then the computer can run the assembly language pretty much directly. There are some exceptions to this. Feel free to ask me more about it if you want to understand how then assembly language gets converted into stuff that actually the computer runs. But for the most part, this is the paradigm we're going to talk about. So in order to run a C program, you need to first write it. You can write it in a text editor. You can write it on a sheet of paper and scan it into the computer, as long as the text has made it in there somehow. And then you run this program called a compiler to convert the text file that you've created into these assembly instructions, and then you can execute the program, which really just contains the assembly instructions which your computer will then understand. Now, in this class, we're primarily going to use two different compilers. For our purposes, they're largely interchangeable. One called Clang or CLang, and the other called GCC. It doesn't matter which you use, but you may find that over time, trying to run in the other, they'll give you different error messages about mistakes you've made, and you may prefer the error messages of one for the other. There are more significant differences, but we'll perhaps leave that to a longer discussion later. In contrast to compiled programs, programming languages, there are also interpreted programming languages. Python is a good example of a programming language that is usually interpreted. What this means is after you've written your Python code, you run the Python program, and as your program is running, there's continuously a translation process that's happening. So it's as you go, the Python program is converting your Python code into assembly instructions. So rather than compiled C, which is you run the compiler once, and then you run the machine code instructions whenever you like, in Python, you run the Python program, which is continuously, as your Python program is going, converting the Python code into assembly code. So these two things are not entirely separate, but they're useful at a high conceptual level, to think about what's going on behind the scenes. Now, the C programming language was born to two very prominent computer scientists, Brian Kernighan, who's now at Princeton, and Dennis Ritchie. And in fact, because you guys are so special, I decided to track down Brian Kernighan to give us a bit of a message for the class.
Hi to all the students in Foundations of Algorithms at the University of Melbourne. I'm Brian Kernighan. I teach computer science at Princeton University in the United States. I wrote the first book on C along with Dennis Ritchie, and I helped build some of the early Unix tools like the ARC programming language. I hope you're all enjoying learning everything there is to know about algorithms. Good luck with the rest of your semester.
Fair. Accidentally cut that bit off. Anyway, so while Brian Kernighan did not create the C programming language himself, he was the author of the foremost textbook by which most people for many decades learned C, including myself. I found an old copy in one of the physics labs in my first year as a student here, before I was even taking computer science, and learned C that way. Fortunately for you today, you've got some more modern resources, but I thought it would be fun to get that message from one of the early people in the field regardless. And so now we are finally ready for Hello World. This, for those of you who have not taken a formal programming class, is traditionally the first program that you will write when you're learning any language. It is a program that is, all it's designed to do is to print the words, to display the words of Hello World on the screen. Yes?
And funnily enough, apparently it was the C programming language that came up with Brian into this.
Yes, so this idea of the Hello World program originally does come from the book, The C Programming Language. And I think if I can find my copy, which has disappeared somewhere, I'll bring it in for the next class. So, in order to get started writing a C programming language, all we need is a text file somewhere. Now, I will warn you that Microsoft Word does not create text files. It creates Microsoft Word files, which behind the scenes actually have a whole lot of different stuff in them. So you need a text editor that will just write plain text. Now, in this class, we'll have a few ways for you to do this. You can log on to Ed, and then you won't need to worry about a lot of this stuff. You can download Visual Studio Code, which you'll see in some of our demos, which will allow you to run the text editor on your own machine. But I'm going to, for the purposes of some of our classes, also use a website that kind of imitates what would happen on your computer. And this one is called vscode.dev, or the particular version of vscode.dev that I'm using is actually called cs50.dev. So I'm going to go to a new website over there and just visit cs50.dev. You'll see ChatGPT in the corner there. We'll talk about ChatGPT later, but I do use it every day, and so should you be, but for not completing your assignments. So we're going to log in. And then, here is a version I prepared earlier. So in the interface, you're going to see a few different windows. So on the side, you'll see a file browser that allows you to navigate the files and folders that are present in this. For the web version, it's a special version of your file system, not the one on your own computer. So don't get confused expecting it to show you the files on your own hard drive. These are files stored on the cloud. In the bottom is a terminal that allows you to type commands into a program we call a shell, which instructs the computer on what you want it to do. And then over here will be our main text editing area. So I am going to go ahead and inside my FOA folder, I'm going to create a new file, and I am going to call it helloworld.c. Now, there is nothing special about a .c file other than you're reminding yourself that this file is probably going to contain C code. Otherwise, it's just an ordinary text file. So, now that I've opened helloworld.c, it's time to actually start writing some C code. Now, be warned that some of the code that I write, we're not going to explain in full until later. It's going to take us a number of classes to get used to C syntax. So let's start off, and I'm going to tell the computer a few basic details that need to be included into my program. So I'm going to tell it where the main part of my program is, and then use the printf function, and we'll talk more about functions soon, in order to display hello world to the screen. Okay, now remember, in order to actually run a C program, what did I need to do? I needed to use a special program called a compiler. So I need to run my compiler. And to run my compiler, I'm going to go down to the terminal window where I can run some commands. And I'm going to run the command just like you saw me doing in the early part of the class. And the two compilers that I could use were clang and GCC. So I'm going to type GCC and just press enter. Okay, no input files given. I haven't told it what I actually want it to compile yet. So I could run GCC helloworld.c. No such file or directory. Why is GCC complaining? Anyone know already? Okay. Say, what was your name?
I'm also Alex.
Alex as well. Okay, it makes my life easy and hard.
Yeah.
What is the problem?
Are you in the wrong? Do you need to give instructions to how it can navigate to the?
Yeah, I haven't told it where in my directory structure this file is actually located. So I'm now going to show you, I'll show them to you more formally later, but a few commands that you can use in the terminal. So the first one I'm going to show you is just clear. Does what it says on the tin. Now the next one is PWD, print working directory. So if I press this, it'll tell me where my terminal is currently looking for files, where it currently is. And so in this case, my current working directory is just 2287839, which matches up to this. And I can see that within 2287839, there is a subdirectory called FOA, and only inside FOA is helloworld.c. So what I need to do is I need to change directory from my current directory to the place where my code is. And so I'm going to run the change directory command, which is just cd for change directory, and I'm going to tell it FOA. So you can see now my little prompt there has changed to show that I'm in FOA. And what I can do now probably makes sense, and I tend to do this all the time just to check that what's going on, is I'm going to list all the files in the directory on the terminal just to know I'm in the right place. So I'm going to run the ls command. And then you can see that inside that folder, I have helloworld.c and I have lecture 1. Okay, now I'm ready to run GCC. And I'm going to run hello world.c. Now, something you might have noticed if you were paying close attention, I didn't actually type in all the letters of hello world.c. I was able to get the computer to finish it very quickly. Now, that is a trick that all of you should know right from the beginning, and it's called tab completion. If you're in the middle of typing something and you think there's a logical and easy way for the computer to fill it in, try pressing the tab key, and in many instances the computer will fill in the rest of the word, particularly if there's only one option. If there are multiple options, you may need to press tab twice, and then it might let you choose between them, but that's a trick for later. Okay, GCC, hello world.c. Okay. It didn't do anything. Alex? Tell me what's going on. This Alex, with the microphone, Alex.
Clue.
Well, do you think it did anything?
No. Well, there's no output that I can see.
Well, what did the command do? What was I trying to do? What was I trying to accomplish? Just with that command, not overall.
Oh, you were just trying to translate the code into...
Yeah, make sure you speak into the microphone.
Yeah, you're just trying to translate the code?
Yeah, so what I wanted the computer to do was to translate the code from this kind of C syntax into that assembly language that it can actually understand. And if we look over here, what do we see?
A new file?
There's a new file, a.out. Okay, now let's click on a.out. This file is not displayed in the text editor because it's either binary or... Okay, so essentially what I think has happened is that our compiler has actually gone and created a new file that contains the contents of the conversion. Now, we didn't tell the compiler what to name it, and so it just names it a.out. And so that's another place that you might go wrong when you're running the compiler. But now, I can try running a.out. Oh no, a.out command not found. Alex, now what's happening? Well, let's read the message carefully. Command not found. What do you think the computer thinks is happening?
They can't find the translated code this time?
So not quite. When it says command not found, that means it's already... What was your name again, just so I know for future? Yeah. Vincent. We'll call on you another time. But essentially what's happening here is when I used ls and pwd and cd, these were commands that were kind of built into the terminal, built into the shell program. But a.out isn't built in. We somehow need to tell the shell program that a.out is actually a file and we want it to run the file. So the way we're going to do that is by using this syntax, a dot and then a slash, to say, look in the current directory for a file with this name, and now we can give it its name. Now let's run a.out, and then we see hello world. Now this is a bit ugly. What's ugly about it? Alex, you still got the mic.
By some things that weren't a part of the, or wasn't intended to be part of the output?
Yeah, so now we've got another line that's FOA, so we probably want to separate that prompt from the rest of the output of our program. So now we're going to use a new line character. Now, let's see what happens if I do this. One way to learn how to program is to experiment and get things wrong. You don't always have to get it right. And I'm going to get an error. Error, expected semicolon before close var token, and then it tells me that this happened on line 5. Unlike in Python, where it matters how many spaces and tabs, in C, you don't have to worry about spaces and tabs. However, if you do that in the middle of a string, it'll break. So if I were to put the semicolon on a new line here, it'll still run. If I put that part on a new line, it'll still run. Still does the same thing. But if I want to figure out how to put a new line in there, it didn't work when I broke up the string with a new line. So I guess I have to try something different. How do we do this in Python or in another programming language? What do we normally do? We need a /n. So we have a special character that denotates new line. So now let's try that again. There we go, hello world. Now one other kind of dissatisfying thing is that the program is named a.out, and so I'm going to try something different. I'm going to add what we call an argument to the program. This is just saying we're going to give it an additional piece of information, an additional piece of input that lets us tell the compiler what we want the program to be named when it produces it. So in this case, I'm going to write a dash and then an O to say the information that I'm about to give you is going to be the name of the output file, and then we'll call the output file hello world. So now if we look here, we can see it's created hello world. Okay, so now we have our program. It's called hello world. We're doing pretty well so far. But just because we can doesn't mean we should. So we still have this separated like printf and hello world on separate lines. That's bad programming practice because it obscures from the reader and from us what is actually going on in the program. So as much as we could kind of write it like that, an ugly C program is not necessarily a good C program. So we're going to take it back to like this. Now, one other thing, a common mistake that many people make, and that you really do not want to make, is the following. Ooh. Give me a second. Okay. We are ready to make the mistake now. I've saved my work in a backup. Okay. Someone else who doesn't have the microphone yet, okay, let's pass it back over here, this guy with the glasses. Yeah. What's your name? There we go. We'll be on in a second.
Sure. My name's Aaron.
What have I just instructed the computer to do? I haven't run this line yet.
You've instructed the computer in the terminal to rename it to the same name of the file.
Yeah, so I've told it to take the program that I've written, convert it into assembly code, and then put the assembly code in a file named helloworld.c. So let's see what happens. Oh, GCC has actually gotten smarter than last time I used it. Let's try it with Clang. Clang might not be that smart yet. There we go. Ah. And there goes my program. I have accidentally overwritten my program with the compiled version of the program. And now all my hard work and code is gone. Now we can talk a lot about how to back up your code appropriately and how developers actually do this. But if you do this on your assignment, and you have not backed up your assignment properly, and your compiler has not stopped you from doing this, you will lose your work. Now, again, we'll talk about ways to avoid this happening to you, but just so you know, this is also a good answer to why isn't my code working, or why have things gone wrong. We'll see a number of those types of errors. Now, thankfully, I put it on the clipboard, so we get it back, but be very, very careful about that. Although I am glad to see that GCC now tries to stop you shooting yourself in the foot. But one thing about the C programming language is it is filled with ways to allow you to shoot yourself in the foot, and part of learning to program in a language like this is learning about those kinds of, the ways that you can mess up, and the reason why the computer might actually allow you to mess up. So C takes the general presumption that you know what you're doing, even when you don't, and allows you to manipulate things in whatever way you wish, even when sometimes that's inadvisable. Okay, so that was just a text file. And so we're going to compile our program using the shell, which is a separate program running on the computer, which actually takes in our commands. So where I was typing my commands in the terminal, that in itself is a program that someone probably wrote, and also probably wrote in C. Most of the shells are themselves written in C. So if you're asking, like, why are we learning this complicated language that allows us to do stupid things like overwrite our programs with themselves, it's because this is the programming language in which a lot of modern infrastructure is actually built. Okay, we talked a bit about that. Why can't I run the command directly? it's because we need to give the operating system, we need to give the terminal the path to the program. So that's why I have the yellow brick road there. Dot is shorthand for the current directory, and then the way we're going to denotate a particular path to the computer is by having a slash to denote subdirectories. So for example, let's go out again, and let's see my current directory. So I'm back in the 2287839. Let's clear that up. And now if I type // and press tab twice, it'll show me all the different directories that are in my current, that are spanning off from my current directory. So now if I type FOA and I type / and I press tab twice, I can see all the files that are in the FOA directory. And now if I write hello world, I can actually run the program like that, even not being in the current directory. So the dot is just shorthand for the current directory instead of having to type out that whole thing. But if you wanted to demonstrate it, we could do it that way. And that is the full path. There's no dot, there's no current directory in that. It's just the full, giving the computer the full instruction of where to go, and that'll run as well. Now we are going to spend a little bit of our class time over the next couple of hours, well, not all of them today, don't worry, but going through some basic C syntax. This bit might be a little bit drier because you're actually going to need to know a few basics before we actually can write more sophisticated programs. So firstly, I want to look at one or two features here. So the first is that every line in C must terminate on a semicolon. And when I say line, what I really mean is statement. As we showed before, you can break it up and do it weirdly, but it's all ultimately part of the same idea. So every idea in C is going to be terminated by a semicolon. Ignore that. Every function or every mini instruction that we tell the computer to do is going to be surrounded by brackets. And then every function is going to be enclosed by these curly braces. Is going to look at what we call types in C. Now, unlike in Python, if you want something to be a number or you want something to be a letter, you need to explicitly tell the compiler the type of thing that you're creating, the type of variable. So let's create a new file and just call this io.c. And I'm going to copy and paste all this stuff that we really don't know what it does yet in here and start from scratch with our just basic template. Feel free to do this yourselves. So the first thing I'm going to do is I'm going to create a variable. We'll just call it n. And this will be an integer, or the way we specify an integer in C is with the word int. I'm also going to specify another number called a double. And a double is going to be a type that allows us to contain a number that has a decimal point in it. So an integer really means integer in kind of almost the strict mathematical sense. There are some deviations from the way integers work in maths, but basically it can only contain a whole number, no decimal points allowed. A double is allowed to have the decimal point and some numbers after the decimal point, so like 3.57. Now I'm going to use a function called scanf. Now this is one of the key functions that you will need to know for the mid-semester test and also really to get started with anything. And this is one of the ways of getting input from the user. So do not worry about the somewhat scary looking syntax for the time being. We will explain it all in due course. There we go. So what scanf allows us to do is it allows us to ask the user for input. And so what I've told the computer is I've told it expect the user to enter an integer, which we tell it with %d, followed by a space, followed by a long float, which is really old terminology for a double, for a number with a decimal point in it. Now, in the book, you might see mention of a float, but we're not really going to use them in this class anymore because for the most part, they're not going to be important for our purposes until well after you've finished your degrees. They do get used a little bit now for some AI stuff, but we can talk a bit more about that later, or ask if you're in the more comfortable tutorial, feel free to ask Tracy. So we have two things that are really paired together that we've done. The first is to get input from the user and then to spit it back at the user. So scanf just gave us a blank line in which we input 5 and 32.5, and then printf allowed us to spit it back out. Now, if we wanted to be a bit clearer to the user, what we might do is please enter to numbers an integer and a double with a space between. And now if I compile it, we can now see that's looking a lot cleaner. Now, the only problem here is now I have to kind of scroll to see both sides of my code. And so what we typically encourage you to do is to have no more than 120 characters on a line. And if you want to break up a string between two lines, what you can do, and I did this earlier before if anyone was paying close attention, is you can put a backslash and that will break up a line for a string. So we can see if we run this again, oh, now there are a bunch of spaces here. There we go. Let me recompile that. There we go. And you can see it still does the same thing, only now it's more visually readable. So along with the %d and the %lf, there are a whole bunch of different format specifiers that you need to include to tell the compiler what kind of type it's dealing with when it reads something in, or what kind of type it needs to be reading from when it puts something out. Now, one other kind of tricky feature about scanf that will become clearer why in week 3 or 4 is that for scanf, for most variable types, you need to include an ampersand before the variable name. However, for printf, there is no ampersand. You just write the variable name. There is one exception to this, and we will learn the exception later in class. So if any of you have spent too much time on the internet before, you might have seen this acronym. It was particularly prominent in the late 90s and early 2000s when, who was born later than the early 2000s? I think we're mostly Gen Z-ish now, getting there, Gen Alpha. Anyone identify as Alpha? No one yet. I think they might still be 2 years too young. Don't worry, I won't say anything bad about them for the moment. They were all at the Billie Eilish concert with me last night. So you might have seen this acronym RTFM, which is essentially saying, you know, if you're a programmer, if you're a person on the internet, you need to know how to read the manual. Why are you asking me when you could have looked it up yourself? Now, there are a few ways that you could approach this. So the first is to literally go and read the manual. But thankfully, the manual is digitized and available if you just look up the relevant bits. So let's go here. And what do we think the manual command is called, if you had to guess? Help would be pretty good. So let's try help. Well, that gives us something, but what help is actually doing is it's giving us information about the shell. If we want to get information about all the programs installed on the computer, including the C standard library, which is the C set of functions that come built in, we're going to use the man command. And so we're going to, in this case, ask for, let's do man printf. There we go. And we can see that this is the general commands manual, and this is actually reading from section 1 of the manual. You can see that 1 is in parentheses. Now this is a bit of a trick actually, because there is not only a command in C called printf, but there's also a program on the computer called printf. And so this is actually the wrong manual page. So we are going to actually have to specify for the manual which section we want in order to look for the C commands. Now, if I remember correctly, it is section 3. There we go. So now we can see we're in section 3, and this is the library functions manual. So it's the manual of functions that are part of the C library. And now we can now see, that it's going to give us all the details of the printf command that looks very similar to the one we just typed in. Now, if we take a look at the description, produces output according to a format as described below. And then this man is really long, but we can kind of scroll down up to the point where we see something familiar. Now, reading through the man page can be a bit of a pain. So another option for us is actually to look at a simplified version of the man pages that has been written just for classes. So let me show this on the other computer when it loads. Whoop. There we are. This is the CS50 man pages, which provide user-friendly versions of all the manual pages that you might need for this class, with a few exceptions. So if I type in printf here, see printf, and there is a much more simplified version of the man page that you can look up. Now, on top of that, we also have access to another unreliable but sometimes very useful source of information that we as programmers are likely going to use in our careers now. Anyone know what that is? AI. Okay, let's try ChatGPT. Okay, let's do that. And let's switch it off O1 Pro. That is too expensive. So let's do explain the syntax of printf to me with the most common things I'd need to use different types with it. And this is actually going to be pretty good. Now, what I will say is trust but verify. So generally, ChatGPT is pretty accurate with a lot of basic programming things, but you can't rely on it. You might want to cross-reference this against the manual or give different things a try. So one nice useful thing it's done is it's actually produced a table of the format specifiers that we might want to most commonly use. So I do really encourage the use of AI in general, just not for completing the assessment tasks, because if you complete your assessment tasks using ChatGPT, then you won't have learned anything. And that's aside from all the other academic integrity concerns. So here is a list of all the different operators that we now might want to use now that we've started to come up with some types. Now, for the purposes of our class, we are going to focus on this set of operators. So addition, subtraction, multiplication, division, and also modular arithmetic that you can do with the modulo symbol. So hopefully most of you have seen the modulo operator at some point in your programming career. If not, we will go over it at some point soon. We will also focus on some of the comparison operators for checking equality, for checking if something is greater than or smaller than, and checking for non-equality as well. And this leads into our broader discussion of types, which is where we're going to close the class today after we've had a bit of a chat about some of the types in the C programming language. So the first type that we encountered in our Hello World program was the character type. Now this contains symbols, some of which are letters, some of which are numbers, and some of which are things like exclamation marks, question marks, etc. Now one thing to be very careful about, and some of you who've seen this in other programming languages might already be familiar, is there's a difference between the symbol for the number 9 and the actual quantity 9. You can draw, like, there are other languages that have different symbols for the number 9, like Roman numerals, for example. And just because we want to print out the Roman numeral for 9 doesn't mean that the computer inherently can do arithmetic on it. So if we're including something in a pair of quotation marks, either single or double quotes, the computer is not going to treat that as a numerical quantity, but rather as a symbol. Just like X, the Roman numeral, is the symbol for the number 10, the character for the number 1 and the character for the number 0 is just a symbol for 10. It's not the same as the computer actually storing the quantity 10. So ASCII, the American Standard Code for Information Interchange, is going to map all of these different symbols, exclamation marks, the symbols for numbers, the symbols for letters, to an internal number that the computer is going to store, so that inside the computer it knows, okay, if I have the number 65 that's stored inside my memory somewhere, what I want to show on the screen is a symbol that looks like the Western letter, like the English letter A. If I see the number 66, I want that to be equivalent to an instruction to me to print out the number, the English letter B. Now, the reason we need to do this is because inside the computer, there's no actual letter storage place. There are just numbers that we can store inside the computer. And so standards organizations came up with an agreed set of conversion from numbers to symbols, and ASCII was the simplest one. So this leads us to, there's a bit of a delay, to the character type. The character type is the data type that C uses to store individual singular characters. So this might be the symbol for a 1, this might be an exclamation mark, this might be the letter A. And behind the scenes, this is indeed what's happening. You can see 65 is indeed the number for the letter A, 66 is the number for the letter B, but also confusingly, can take a little time to wrap your head around, 49 is the number for the symbol that looks like a 1. Again, that's the symbol for a 1, not the quantity 1. And these go up, the normal ASCII character set goes all the way from 0, which is called the null byte with a single L, all the way up to 127, which is a special delete character. Now, a bunch of these characters, in particular the ones in gray, are what we call non-printable characters. They're like, if you ask the computer to print out the number, the equivalent of the number 26 in our symbol conversion table, you'll get either a weird symbol on the screen or a question mark or a blank space or nothing at all, because there's actually no actual symbol to print out there. These were used in early versions of computers to help instruct the computer how to lay out some of its output and also to enable it to take in certain commands. So we're not going to worry too much about those. Now, there's also what we call extended ASCII, which goes up to 255, and that is indeed the maximum size that a character can hold. A character can hold any number from 0 to 255, and that number is going to represent something from this chart. So that seems straightforward enough. Nothing super exciting there. Okay, let's do some maths. Who's got one of these at home or on their wrist? Not all digital already? Great. We know what a clock is. Thank God, I thought I was going to have to spend half an hour on that. But what you may not have spent a lot of time actually thinking about is how to do arithmetic with a clock. So what happens when you get to 11 a.m. and you add 2 hours? It's a dead easy question. 1 p.m. And when you get to 1 p.m. and you need to go back 2 hours? 11 a.m. So clearly something funny is going on here that you internally just know how to do, which is when we hit 12, we kind of reset. Again, we reset to 1. And so this is actually what we call modular arithmetic, or some people call it clock arithmetic, which is an informal term. And it's this idea that we can have a closed set of numbers that when we hit the biggest number, instead of going bigger still, we just wrap around again. And inside the computer, this is actually how most numbers are going to be represented, at least in the C programming language. Our standard integers are going to be represented this way. So as my, at the time, 4-year-old first cousin asked me, why are we doing this? Is there really a limit to how high computers can count? Hannah, okay, is there a limit to how high a computer can count? And if so, why?
I think like there must be a limit, but it depends on like how much time it takes.
Okay, so one answer is if we tell our computer to count as quickly as it can, to keep outputting numbers, depends how much time is available. What other limitations might there be?
Like the I don't know, maybe like electricity, temperature.
Kind of. What about the amount of memory your computer has?
Oh yeah.
So do you know how much memory your computer has? Roughly, like your own laptop. Tera, mega, what's the word that I'm missing at the end there? Tera, giga, mega, bytes, yeah, megabytes. And so that specification tells us how much memory a computer might either have on its hard drive or indeed in its RAM, its working memory. And so if we have a number that has more digits than the amount of digits that our computer is able to store in its memory, we're not actually going to be able to do a computation in it. Now let's say we use all the digits but 1, and then we add 10 to our number, we're still not going to be able to store the result. So there seems to be some kind of like hard physical limit on our actual computers as to how high the computers can count. So that in itself is kind of interesting. So in order to deal with this kind of problem, and also in order to make computers efficient, what we actually do is we cap the computers. We cap how high a standard number in the computer will go. And at least until the mid-2000s, the cap that we used to do was 2 to the 32. So when we hit 2 to the 32, we go right back to 0. Now, who knows why we might count in powers of 2? So here I'm going 0, 1, 2, 4, 8, 16, 32, etc. You guys I know the answer. Someone else. What was your name?
My name's also Alex.
Oh my God. Okay, put your hand up if your name is Alex. Is it? Okay, so all the Alexes have clustered in one corner of the room.
It seems kind of natural because binary corresponds to powers of 2.
Yeah, so what's happening inside the computer is the way we store numbers is using switches that are essentially on or off. And each of those switches has 2 possible positions, either the on or the off. Bless you, Liam. So what we do if we have 2 switches, then we have 4 possible numbers that we can represent, because we've got 4 possible states. If we have 3 switches, then we have 8, 2, 4, 8. We have 8, sorry, maths. We have 8 possible combinations that we can represent. So what we're saying with 2 to the 32 being our largest number is we're saying, okay, reserve the equivalent of 32 switches inside the computer to represent each number. And we're going to use the way that a switch is physically instantiated, we will talk a bit about later in semester. But for the time being, you can imagine that we're going to use 32 of these to represent any given number. But of course, the one number that's really important for us to represent is 0. So we've actually got 2 to the 32 minus 1 other numbers that we can represent. And so just dealing with positive numbers, this takes us all the way from 0 to 2 to the 32 minus 1. Now, as I just said, we're going to use binary to represent these. So if we were going to write this out, we'll talk about how to convert from decimal to binary a little later. 0, 1, and then 1, 0 is 2, 1, 0, 0 is 4, 1, 0, 0, 0, 0 is 8, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0 is the largest power of 2 that we can get. So that would be 2 to the 31 if I counted my zeros correctly. Now to get the other numbers, we can start including some other ones in those numbers, and we'll discuss which ones to flip as we go along. Man, that was a lot of zeros. I lost count there. Hopefully someone did a better job than me. But we have a problem. So far, we've only spoken about representing positive numbers, but we probably want to be able to represent negative numbers as well. So one way of doing this is let's just split all our possible numbers in half, because we know that we have 2 to the 32 possible different switch settings that we have. And let's say half of those switch settings will be for the negative numbers, half of the switch settings will be for the positive numbers. So we'll use the first half just as before. So going 0, 1, 1, 0, and after 1, 0, who knows what comes next? Not on that. After 1, 0, how do you do 3 in binary? Does anyone know? 1, 1. And then after 1, 1 is 1, 0, 0, and then 1, 0, 1, and then 1, 1, 0, and so on and so forth. But when we get halfway, we're actually going to say, okay, now we're in the negative half, but instead of starting from -1 down at the bottom, we're actually going to just go counterclockwise. And so all ones is going to be -1. And then all ones and a 0 is going to be -2. And then all ones, a 0, and then a 1 will be -3. And all ones and 2 zeros will be -4. And so it's essentially mirroring the pattern that we have on the other side, just flipped. And so we're going to call this 2's complement representation, and that'll be something we'll talk about again, how to do that conversion in detail later. But what we'll say is that this is what we call an unsigned integer, because it doesn't have a positive sign or a negative sign, it's just only integers. And this is what we'll call a signed integer, because it is allowed to have a negative sign. And you can actually specify in C, instead of just int, you can write signed int or unsigned int, and that'll change the maximum number that your integer is allowed to go up to. Was that a question at the back? Or just a stretch? What was your name? Yeah? Ray? Awesome. Okay, but 2 to the 32 is pretty small. So if you were to actually figure out what the number is in terms of bytes, it's going to be a small number of gigabytes. So you're not going to be able to go easily over 4 gigabytes of memory in your computer, assuming that each location in your computer's memory has its own address and is represented by one of these numbers. So 2 to the 32 is pretty small. Who remembers what 2 to the 32 is off the top of their head? Yeah, it's 4 billion, so that's 4 gigabytes. 4,294,967,296. There we go. So that number, 4 billion, is big, but it's not that big. And so what modern computers have done is they've actually said, okay, given that the numbers we want to deal with are much larger, let's have the standard size of a computer number actually have 64 bits, so 64 switches. And a bit is just going to be the name that we use for one of these individual switches, 1 or 0 inside the computer. And so now when we do arithmetic, we're going to divide up 2 to the 64 for an unsigned integer into all the positive numbers and 0. And then if we are using a signed integer, we will use 2 to the 64 minus 1, sorry, 2 to the 64 will be split evenly halfway along between the positive and the negatives. But this is still not big enough to represent everything that we'd want to possibly represent with our computer. How do we get bigger numbers than 2 to the 64? Anyone have a creative idea of how we might do this if the default integer size is 2 to the 64?
You could use something like hexadecimal.
Like?
The base as 16 instead of 2.
So rather than using a different base, what we might want to do is maybe think about how we can use different integers together. So can you maybe expand on that idea a little more? If a standard integer is 2 to the 64, what could I do if I want to represent something bigger?
You can just increase it.
Well, we can't increase it because that's physically how we built the computer, but we can store more than one 2 to the 64-bit number on our computer.
You can use 2 of them to like denote the higher amount.
So that's essentially what we'll do, is we'll use collections of numbers to represent larger numbers. So, for example, just like you have a ones place and a tens place and a hundreds place, and you can specify the size of the number in the hundreds place, we could use one of our clocks to represent the billions place, or the hundreds of billions of place, or the trillions place, and by combining different clocks, different integers together, we can overall represent a bigger number. And so we will get to some of the implications for what this means for our programming in the next lecture. Thank you very much. I hope you enjoyed day one of Foundations of Algorithms, and I will see you in a couple weeks.